Australia's National Science Agency just did something that sounds like it belongs in a science fiction movie, and in this video I'm going to break down exactly what happened, why it matters, and whether the bold claim in this title, that ground data centers are becoming obsolete, actually holds up once you look past the headlines. CSIRO, which stands for the Commonwealth Scientific and Industrial Research Organization, has built and delivered a piece of hardware that beams entangled particles of light from a ground station all the way up to a satellite hundreds of kilometers overhead. Stick with me till the end of this video because I'm going to walk you through the actual science, the real-world problem this solves, who else in the world is racing to solve the same problem, and what this technology can and cannot actually do right now in 2026. Let's start with what CSIRO actually built, because the language around quantum technology tends to get exaggerated very quickly online, and I want to keep this video grounded in what has actually been confirmed. CSIRO researchers designed and built two portable, high-flux entangled photon sources, which the agency has named the CSIRO Quantum Light Source. These devices were developed as part of a project led by Australia's Defence Science and Technology Group, based in Adelaide, and the technology was delivered to that group in July 2026. The core idea behind this device is something called quantum entanglement, which is a strange but well-established property of quantum physics, where two tiny particles, in this case, photons of light, become linked in such a way that a change to one particle is instantly reflected in the other, no matter how far apart they are. In CSIRO's setup, one of these entangled photons stays on the ground at what is called an optical ground station, while its entangled partner is beamed up to an orbiting satellite hundreds of kilometers away. Despite that enormous distance, the two photons remain entangled, and this entanglement allows a secure communication link to be established between the ground and the satellite. What makes this particularly powerful is that quantum entanglement is extremely sensitive to interference. If anyone tries to intercept, tap, or tamper with that link, the quantum state of the photons changes immediately, and that disruption can be detected right away, allowing the system to automatically switch over to a different, uncompromised channel. This continuous process is called entanglement distribution, and it is essentially what makes this system spoof-proof. Now let's talk about why CSIRO built this in the first place, because understanding the actual problem makes the solution make a lot more sense. Almost every part of modern life quietly depends on extremely precise timing signals broadcast from satellites. This system is called the Global Navigation Satellite System, or GNSS, and it works by having satellites carrying atomic clocks transmit time-stamped signals down to receivers here on Earth. The Global Positioning System, or GPS, is the version of GNSS that most people in Australia and the United States are familiar with, but it is only one of several GNSS constellations operating around the world. When these systems work properly, they underpin navigation for ships, aircraft, and vehicles. They synchronize power grids, they timestamp banking and financial transactions, and they help coordinate emergency services. The problem is that by the time these satellite signals reach Earth, they are extremely weak, and that weakness makes them surprisingly easy to disrupt. There are two main ways this happens, and CSIRO's own researchers have been very clear about both. The first is jamming, which simply overpowers or blocks the weak satellite signal so that receivers cannot pick it up at all. The second and more dangerous method is spoofing, where an attacker transmits a false but convincing signal that tricks a receiver into accepting the wrong location or the wrong time. Jamming devices are illegal in Australia and in many other countries, yet they are still obtained through illicit channels, and sophisticated spoofing, while harder to pull off, is becoming more accessible as software-defined radio technology and open-source tools spread more widely. This is not a theoretical or future risk either. GNSS interference is already happening around the world today, and in contested environments, these signals are being disrupted deliberately, sometimes as an act of open conflict, causing critical systems that depend on them to fail. So this is the real gap that CSIRO's quantum light source is designed to fill. Instead of relying purely on the traditional radio frequency signals that are vulnerable to jamming and spoofing, this quantum-enabled timing signal creates a secure and highly interference-sensitive channel between a ground station and a satellite. If someone tries to mess with it, the system knows immediately, and it can respond by switching to a secure alternative rather than silently accepting a corrupted signal the way conventional GNSS receivers often do. CSIRO's technical lead on this project, Matt Broom, described this achievement as a significant milestone in the development of quantum-secure time transfer in Australia, and he specifically noted that this work puts Australia on a path toward a more resilient future in global positioning technology. It is also worth mentioning where this technology actually came from, because it did not appear out of nowhere. The project began as a collaboration with Heriot-Watt University in Scotland, and CSIRO's engineering team took the source design thinking developed by their Scottish counterparts in laboratory conditions and set out to translate it into something field deployable. That distinction matters a lot in quantum physics. Because building something that works inside a carefully controlled lab environment is one challenge, but compressing those same fragile optics into a ruggedized box that can survive being deployed at a real optical ground station out in the field is a completely different engineering problem. CSIRO's team appears to have solved that problem, delivering a system that is portable and, according to the agency, easily deployable. Now, while this project was developed primarily with defense applications in mind, and it is specifically intended to support the Australian Defence Force, in environments where GNSS signals might be degraded or completely denied, CSIRO has been quite clear that the underlying capability is not limited to military use. The exact same secure timing that would allow military systems to keep operating when GPS is jammed or spoofed also has direct applications for civilian infrastructure. This includes communications networks, power grids, transport systems, and financial services, all of which depend on that same precise timing signal to function correctly. If a power grid's synchronization signal gets spoofed, or if a financial exchange's time-stamping system gets tampered with, the consequences can ripple out far beyond a single satellite receiver, which is exactly why this dual-use nature of the technology is such a big part of the story. There's another angle to this that is worth highlighting, and that is what CSIRO calls sovereign capability. That develop this kind of specialized in-house capability now are less likely to find themselves dependent on foreign suppliers for critical infrastructure components later. CSIRO has framed this project explicitly as strengthening Australia's position in that broader global race. Now let's zoom out for a moment and look at what other countries are doing in this same space, because CSIRO is far from the only player working on quantum-resilient positioning and timing. In the United Kingdom, a company called Inflection has already flown a competing quantum navigation system called QINS, which was backed by several million pounds of funding from UK research and innovation and completed test flights back in May of 2024. Meanwhile, in the United States, the Department of Transportation has awarded significant funding across multiple programs aimed at reviving older ground-based timing systems like ELORAN, as well as developing backup timing capabilities using low Earth orbit satellites. What we can say is that CSIRO's entangled photon method appears to be the first of its kind to actually be delivered to a defense customer in a portable, field-ready form, according to CSIRO's own official release. Now let's address the elephant in the room, the specific claim in this video's title that ground data centers are becoming obsolete because of this development. I want to be completely transparent with you here, because that is a dramatic framing, and it is worth examining critically rather than just repeating it uncritically. What CSIRO actually built and delivered is a secure timing and interference detection system designed to protect GNSS signals from jamming and spoofing. It is not a system designed to replace data centers, it is not a bulk data transmission network, and it is not, at least based on everything that has been publicly confirmed so far, intended to move large volumes of information the way a data center does. What this technology does do is protect the extremely precise timing signals that many data centers, power grids, and financial systems rely on to stay synchronized and secure. Banks, telecom networks, and power utilities maintain enormous, expensive ground-based infrastructure, partly because they need an unbreakable chain of trust for timing and coordination. If quantum-secured timing links between ground stations and satellites become mature, reliable, and widely deployed. The argument some researchers and futurists make is that is a genuinely interesting long-term possibility, but I want to be honest with you, that is a speculative extrapolation of where this technology could theoretically lead over many years, not something CSIRO has claimed will happen, and definitely not something that is happening today. let's take a moment to actually unpack how quantum entanglement itself works, because I think a lot of people watching this video have heard the term thrown around without ever getting a clear explanation of it. But it does create a correlation between the two particles that is fundamentally different from anything in classical physics. One half of that entangled pair then gets sent up toward the satellite while the other stays on the ground, and the ongoing correlation between the two is what gets monitored to detect any tampering. Quantum entangled systems behave very differently. Let's also talk about who benefits from this technology if it eventually does get deployed more broadly, because the applications extend well beyond a single defense program in Adelaide. Aircraft and ships rely on GNSS timing for navigation and coordination, and any disruption to that timing can create serious safety risks, not just inconvenience. Emergency services coordinate response times and locations using the same underlying timing infrastructure. Financial markets, particularly high-frequency trading systems, depend on extremely precise timestamps to ensure transactions are processed fairly and in the correct order, and any manipulation of that timing could theoretically be exploited for financial gain. Power grids use precise timing to synchronize electricity generation and distribution across wide areas, and a timing disruption at the wrong moment could contribute to instability or outages. When you start listing out all of these dependencies, it becomes a lot clearer why a government science agency would treat secure timing as a national security priority rather than a niche academic curiosity. I think it is also worth addressing a very reasonable question that some of you might be asking right now, which is why any of this matters if GPS has apparently been working fine for decades already. The honest answer is that the threat landscape around satellite navigation has changed significantly in recent years. As geopolitical tensions have increased in various parts of the world, GNSS jamming and spoofing have moved from being a rare, exotic threat to something that is documented as an active, ongoing tactic in contested regions. Reports of commercial aircraft experiencing GPS spoofing near conflict zones and of jamming affecting civilian shipping routes have become more common in recent years. At the same time, the tools required to attempt these attacks, like software-defined radios, have become cheaper and more widely available, lowering the barrier to entry for anyone wanting to interfere with these signals. This combination of rising geopolitical risk and falling technical barriers is exactly the kind of environment that pushes government agencies like CSIRO to invest in fundamentally more resilient alternatives, rather than just patching the existing system. Now let's talk a little bit about what happens next, because that is ultimately the question everyone watching this video actually cares about. CSIRO has delivered this hardware to the Defense Science and Technology Group, which means the next phase will likely involve integration testing, further field validation, and eventually some form of operational trial. Although, as I mentioned earlier, no specific timeline for that has been publicly announced. Given how these kinds of defense research projects typically progress, it would not be surprising if broader civilian applications take considerably longer to materialize, since defense programs generally move through extensive testing and validation processes before any component of the technology gets adapted for commercial or civilian infrastructure use. If you are hoping to see quantum-secured timing show up in consumer devices or everyday infrastructure within the next year or two, I would temper those expectations. But if you are interested in where satellite security and quantum technology are heading over the next decade, this is absolutely a project worth keeping an eye on. I also want to mention how this fits into the bigger picture of quantum technology development happening around the world right now, because CSIRO's announcement did not happen in isolation. There has been a noticeable acceleration in quantum research funding and announcements globally throughout 2026, ranging from new regional quantum accelerator programs to fresh government-funded initiatives focused on quantum materials and quantum key distribution systems. This broader wave of investment suggests that governments around the world increasingly see quantum technology, whether applied to computing, communications, or secure timing like what we have discussed today, as a strategic priority rather than a purely academic pursuit. Australia positioning itself early with a working, field-deployed entangled photon system for secure timing is a meaningful data point in that larger global story. Let's also take a step back and look at the broader history of quantum entanglement experiments involving satellites, because CSIRO's work builds on a foundation that has been developing for close to a decade now. Back in 2017, Chinese researchers made global headlines when their MICEUS satellite successfully distributed entangled photon pairs between ground stations located over 1,000 kilometers apart, demonstrating for the first time that quantum entanglement could survive being beamed through a satellite link over such enormous distances. That experiment was primarily a scientific demonstration of quantum key distribution for secure communication, proving the underlying physics could work outside a laboratory setting. What CSIRO has done differently is take that same fundamental principle and apply it specifically to the problem of secure timing rather than general purpose, secure messaging. And just as importantly, they have compressed the hardware down into something portable and field deployable rather than requiring a large, fixed, purpose-built ground station. That distinction between a scientific proof of concept and a ruggedized, deployable device intended for a real defense customer is a meaningful step forward in terms of practical engineering, even if the underlying quantum physics itself is not brand new. It is also worth understanding a bit more about how an optical ground station actually works in this context, since that term comes up repeatedly across the reporting on this project. An optical ground station is essentially a specialized facility equipped with precision telescopes and tracking systems capable of maintaining a stable optical link with a satellite as it moves across the sky. Unlike traditional radio frequency ground stations, which can operate in a wide range of weather conditions, optical links are more sensitive to atmospheric conditions like cloud cover, which is one of the practical engineering challenges that any real-world deployment of this technology will need to account for. This is likely part of why CSIRO has been careful to describe this as a capability that is field deployable rather than something guaranteed to work flawlessly in every single environment and weather condition. And it is also probably why no firm operational deployment timeline has been announced yet, since further testing across different real-world conditions would reasonably need to happen first. I also think it is worth addressing skepticism directly, because whenever a story involves the word quantum, there tends to be a mix of genuine excitement and understandable skepticism from people who have seen quantum computing and quantum technology headlines overpromise and underdeliver in the past. This is a fair concern to raise, and I do not think CSIRO's announcement should be treated as beyond scrutiny just because it comes from a respected national science agency. What gives me some confidence that this particular claim is grounded in real, working hardware rather than pure hype is the specificity of the reporting. This is not a vague announcement about future potential. It describes two named specific devices, a named technical lead, a named partner university, a named defense customer, and a specific delivery date in July 2026. That level of concrete detail is generally a good sign that something real and functional has actually been built and handed over, even though, as I mentioned earlier, the broader civilian rollout and long-term implications remain speculative. Something else worth considering is the economic and industrial angle of this story, since building sovereign quantum hardware capability is not just a scientific exercise, it is also an industrial policy decision. Many countries around the world are currently investing heavily in domestic quantum technology industries, partly because they do not want to be dependent on a small handful of other nations for critical future infrastructure components. By developing, manufacturing, and delivering this hardware domestically rather than purchasing an equivalent system from overseas, Australia is building up local expertise, local manufacturing know-how, and a local supply chain in quantum optics and photonics. Over time, this kind of domestic capability can also spin off into other applications beyond secure timing, since the underlying skills in producing and controlling entangled photons are relevant to a much broader range of quantum technologies, including quantum computing and quantum communication networks more generally. Let me also address a practical question that I think a lot of you are probably wondering about, which is what this means for ordinary people who are not defense contractors, bankers, or telecom engineers. In the near term, honestly, the answer is that this will have essentially no direct, noticeable impact on your daily life. You will not see a quantum-secured timing icon appear on your phone, and your banking app is not about to switch over to entangled photons anytime soon. What this project represents is closer to an insurance policy being built for the systems you already rely on without realizing it. If GNSS jamming and spoofing attacks become more frequent and more sophisticated over the coming years, having a proven, working alternative like this already developed and tested means that critical infrastructure operators have a real option to fall back on, rather than scrambling to invent something from scratch during an actual crisis. In that sense, the value of this technology is less about a dramatic overnight transformation and more about quietly reducing a serious long-term risk that most people never think about until something goes wrong. One last comparison I think is worth drawing here is with the early days of the internet itself, since I think it offers a useful way to frame expectations around this kind of technology. When the earliest packet switching networks were being developed decades ago, almost nobody outside a small circle of researchers and defense agencies had any idea that this obscure government-funded communications research would eventually reshape nearly every aspect of daily life. I'm not saying quantum-secured satellite timing is guaranteed to have anywhere near that scale of impact, but it is a useful reminder that foundational infrastructure technology often starts out looking like a narrow, specialized solution to a specific defense or government problem, long before anyone can predict exactly how far its applications will eventually spread. So let me bring this all together and give you my honest, balanced take on this whole story. What CSIRO actually achieved here is genuinely impressive from a scientific and engineering standpoint. Taking a delicate laboratory demonstration of quantum entanglement and turning it into a portable field-deployable device capable of maintaining that entanglement across a link stretching hundreds of kilometers into orbit is a real technical accomplishment, and it directly addresses a growing, serious vulnerability in the timing infrastructure that modern society quietly depends on every single day. The defense applications are clear and immediate, protecting Australian Defence Force operations in environments where adversaries might try to jam or spoof GPS signals. The civilian implications, while promising, are still largely theoretical at this stage, since no field trial schedule or commercial rollout plan has been announced yet. As for the bold claim that ground data centers are becoming obsolete because of this, I would describe that as an exciting glimpse of a possible long-term future, rather than an accurate description of where things stand right now in 2026. This technology strengthens and secures the timing signals that underpin ground-based infrastructure. It does not replace that infrastructure outright, at least not yet, and probably not for a good while longer. What is genuinely true is that the balance of trust between ground-based systems and satellite-based systems is slowly shifting as technologies like this mature, and that shift is worth paying close attention to over the coming years. If you found this breakdown useful, make sure to subscribe to the channel so you do not miss future videos covering major developments in quantum technology, satellite security, and emerging science news like this. Drop a comment letting me know what you think. Do you believe quantum-secured timing links like this one are going to fundamentally reshape how we think about critical infrastructure security? Or do you think this is still mostly a defense-focused niche technology for the foreseeable future? Your comments genuinely help me decide what topics to dig into next. So if there is a specific angle of this story you want me to explore further, let me know down below. Before I wrap up, I want to leave you with one final thought. Stories like this one are a great reminder of why it pays to look past the dramatic headline and dig into the actual source material, because the real story here is genuinely fascinating on its own, without needing to be exaggerated into something it is not. Australia quietly built and delivered a working, field-ready, quantum-entangled photon system capable of securing satellite timing links against some of the most sophisticated interference techniques available today, and that alone is a milestone worth talking about. Thank you for watching, and I will see you in the next video.